Hey everyone, it's Bradley Bush with another algebra video for you. Today we're talking about polynomials and their graphs, and here is our to-do list. The first thing we'll do is we'll talk about the definition of a polynomial. So this is probably the most mathy part of the video. We talk about the literal mathematical definition, and I kind of break it down with some examples. The second thing we talk about is how do you spot a polynomial? If you're given a function, can you tell if it's a polynomial or not? And if it isn't, why? The third thing looks at the graph of a polynomial so we can spot some classic examples of things that are and are not graphs of polynomials. Well, let's get going. Here is the definition of a polynomial, the mathematical definition. So the part that you look at would be right here. That looks really horrible, and it looks like it's not understandable, but it actually is really simple. So there are three parts. The first part would be the exponents. Let's talk about those exponents really quickly. And I'm going to add 1 right here. I'm going to say this is x to the 0. X to the 0 is just the same thing as 1. In fact, anything to the 0 is just 1. And 1 times anything is just itself. So adding x to the 0 here is just like adding a 1. And multiplying by 1 doesn't change anything. I just want to show you that because technically it is there. And I don't want you to freak out about it if I don't show you that right now. So let's talk about these exponents. The exponents are in descending order. If your polynomial is in standard form, then the exponents will be in descending order. That means the biggest will be at the first, and then you'll go down from there. And you'll often, so our example here counts down by 1. Everyone can count backwards by 1. So if our n, meaning our biggest number we had, was say n is 5, then this first one, n would be 5. This would be 4 or 5 minus 1, which is 4. This is 5 minus 2, which is 3. And it just keeps going dot, dot, dot until you'd have 1. And then here you have the 0 at the end. So it starts at 5 and goes 5, 4, 3, all the way down to, and then there's the 1, and then there's the 0. So that's not a problem, right? Start at the biggest one, and then you just count down by 1s. You don't necessarily have to have all of these terms. You could be missing, say, the 4, or you could be missing the 1. It's okay. It's still a polynomial because as long as the polynomial just follows these general features, you still call it a polynomial. But you could have all of the terms, right? You could have a 5, a 4, 3, 2, 1, and then 0 for the exponents. So the exponents, that's nothing big. Nothing horrible at all. The n is the biggest, and then we count down by 1. So we have 5, 4, 3, 2, 1. And if you look at our example down at the bottom, our n is 3. So let's write that. Our n is 3, so our biggest number is 3, and it's first, right? And then we have 2, and then we'll have a 1 here, and then we'll have a 0 here. Let's write that 0. X to the 0, and this is a 1. We assume anything that doesn't have an exponent has a 1 as an exponent. So there we go. We have all the terms, or all the exponents there, right? 3, 2, 1, 0. Done. So that kind of tells us one specific characteristic of a polynomial. The exponents have to be of the group 0, 1, 2, 3, and on up. You can't have fractional exponents like 1/2. You can't have negative exponents like -2. None of those work. If the exponent is not in this group, 0, 1, 2, and on up, the positive integers plus 0, then what you're looking at is not a polynomial. That's first thing. Second thing we have in here, we have constants. Let's do the constants in blue. So all of these a's are constants. They're just the numbers out front. Just like down the bottom, we have 5, we have -9, positive 9, we have -4, and +6. Here, if we needed to write these, let's write them in blue. This would be A3. This would be A2. So A3 equals 5. A2 equals 9. A1 equals -4. And A0 equals 6. So all of the A's up top and so on down to the end, those are all just constants. And the constants, the only restriction we have on the constants is that they can't be imaginary. But they can be any real number. This E, it looks like an E, it's an epsilon. It means an element of, or it belongs to this group. And this thick-looking R here with a thick left side or double bar left side, that just means real numbers. So all of the A's are the I in the bottom just means there's a subscript. So all the A's are just real numbers. So the thing out front, the constant out front, it just has to be a real number, meaning not imaginary. But you can have fractions, you can have radicals, you can have irrational numbers like pi. You can have a lot of different stuff as long as it's a real number. So that's not bad, right? We've got 5, 9. That doesn't look terrible at all. The thing that kind of throws students off is the part right here, this little subscript. But notice all that subscript is just a label. This n for the first term, a sub n, meaning a with an n down below in the bottom right side, that just means it is the constant that belongs with the n term in the exponent. The n minus 1, that just means it's the constant that is in front of the n minus 1 term, and so on. N minus 2, it's just a label. It's a constant with a label. It tells you which x it goes in front of. That's it. That's absolutely it. So that's not hard, right? A sub 1, that's just the constant in front of the term with a 1 as the exponent. And a sub 0, that's the constant term, meaning it's the term that often is just by itself because we don't see this x to the 1. That's never written. So, and the 0 just means the exponent is 0 on the x. That's why it's not written. So the constants, that isn't bad, right? The 5x cubed, down here our example at the very bottom. 5x cubed plus 9x squared minus 4x1 plus 6x. Sorry, just plus 6 because the x to the 0 isn't mentioned. That's a pretty normal looking polynomial. It's not scary at all, right? So that's it. The last thing of the three things is the variable. We have variables here, x's. Those are just the variables. The last one we don't actually, this one here we don't actually write. So we'll have x cubed, x squared, x to the first power, and then this x to the 0 power we don't write. So we just leave that off. That's your polynomial. That's totally it. Let me finish this down here. N equals 3, so this is 2. So n minus 1 would be 2 here. N minus 2 would be 1. And then n minus 3 would be 0. So there you go. Follows that form perfectly. So it's a very general way. Up here, this is a very general way to describe any possible polynomial. And again, you could just have one of those terms in the circle, and it would still be a polynomial. You could have all of them, and it would still be a polynomial. You could have 3. You could have any number of them that you like, but you don't have to have all of them. You just have to have at least one. Let's talk about, is something a polynomial or not? Now we know what a polynomial is. Let's see if we can spot one. Remember, what we're looking for is exponents with 0, 1, 2, 3, and on up. And the constants in front of the x's have to be real numbers. That's it. All right, let's start. So let's check first, is this first one number 1? Is this one a polynomial? Well, let's look at the exponent. Does that fit the 0, 1, 2, and on up? It does. And let's look at the constant out front, 4. That's a real number. So this is perfect. This is a polynomial. It fits all of the rules that it satisfies the rules that it has to be a polynomial, fits the characteristics. Let's look at number 2. Exponents. -1. Here is going to be a 1. It's implied. And here we have an x to the 0. That's also implied. So the exponents, we have 0, 1, those are okay, but -1, is that okay? Can we have -1 as an exponent? Nope, we can't. So no, this is not a polynomial. Why? Because it has negative exponents. Let's look at the next one. So we can actually stop. I should say that. If we find that a polynomial, or the thing we're given, breaks a rule, we can stop looking. We don't need to keep looking to verify if it breaks a second or third rule. We can just stop because it either is or it isn't. So let's look at this next one. Exponents. The exponents we see here are 1 and 3/4. 1 is okay. It falls in the list of acceptable exponents. 3/4, that doesn't fall into the list of 0, 1, 2, 3, and on up. So we can't have fractional exponents. This is not a polynomial. We can stop looking. Why is this not a polynomial? Because it has fractional exponents. We can't have those. Let's look at this next one. Let's look at the exponents. 4, 2, and here there's going to be an x to the 0. Those all fit the group, so those all belong to the okay group of exponents we can have, so that's fine. Not a problem at all. Let's look at the constants. Radical 3. Is that a real number? Yep, it is. Pi. Is that a real number? It is. Those are kind of weird, but they are real numbers, so it's okay. How about -6? Perfect. So this one is okay. This is a polynomial. Let's look at this next one, our final one. We have an exponent here of 1. And over here, we'll write in the other assumed things. We have a 0 there. It's hard to tell what the exponent is on this radical x to the 5. Let's rewrite this so we can kind of understand what we have there. The square root of x to the 5th can be written in exponent form as x to the 5 halves. So x to the 5 halves, what's the exponent on that? It's 5 halves. That is a fractional exponent. We can't have that. So right there, we have problems. So this is the issue right there. No, this is not an exponent. And why is it not an exponent? Because it has fractional exponents. Awesome. Let's look at some graphs of polynomials and some graphs that are not polynomials, because these are also super helpful when you're trying to decide, is something a polynomial? The graphs of polynomials are smooth and continuous. They're actually the nicest looking graphs that you have, among the nicest looking graphs that you have in algebra, in mathematics in general. So smooth means all of the curves are nice and beautiful, meaning that you don't have abrupt changes that cause kinks or sharp edges. You can turn up and down as many times as you want. You can change direction as many times as you want, but they're smooth. They're kind of gently sloping, or even if they're not super gentle, they're still nice looking. They aren't like this cusp. That's a very sharp edge. Or this right there, that abrupt change. There's no curve there. It's an abrupt instant change. Or like these two, up top or these ones in the bottom or any of these, actually, they're all abrupt changes. We don't have abrupt changes in polynomial function graphs. We also don't have discontinuities, like this jump right here, this break right here. That means it's not continuous. You have to take your pen off the graph to go to the next spot. So polynomial graphs are continuous everywhere, and they're nice and smooth. They could have a lot of curves, a lot of changes in direction, but they still don't have these sharp, abrupt changes in their edges. That's it. Hope this was helpful. Hope you can now spot polynomials and understand what the definition is, and you understand a little bit more about what the graph of a polynomial looks like and what it doesn't look like. If you like what you saw, subscribe to the channel, and thanks for watching.